everyone. It's really exciting to be here. So thanks to all the organizers, especially for setting this up. Right, so my name's Ryan. My co-author Stephen Kell and I are working together on testing debug info for optimized programs. I guess just at the outset, I want to say this is preliminary work that we're still working on this and hoping to submit later this year. But yeah, diving kind of right into this. So if you've ever tried to debug an optimized program before, you have probably seen lots of messages like optimize out or variable not available, or these sorts of things that kind of make you want to sort of pull your hair out or just be very upset that you can't access information that you normally would expect when you're trying to debug. But let's kind of take a look at why this sort of thing happens. So we have a small C code example there on the left. It's just going through a loop, not really that interesting, but we put this through Flag 13 with some optimizations turned on. And if you stare at that assembly long enough, you'll notice that it's actually unrolling that loop. But we'll kind of dive into the details of this example a little bit later on. But one thing I want to just mention right now is that unfortunately it has kind of lost a lot of the debug info. So a lot of the instructions that are kind of the core of that loop have actually been mapped to the wrong source line. So if you were stopping the debugger, it would be showing you the wrong source line. And then also the variable y, which is kind of the core one being updated in the body of the loop, is sort of mapped to the wrong storage location. So you wouldn't be able to access that variable in the debugger if you stopped on some of those machine instructions. And so why does this happen? So unfortunately today, in optimizing compilers, especially the kind of key ones that everyone's using, Clang, GCC, and such, they have such complex optimizations that unfortunately the debug information kind of gets corrupted or lost along the way. And part of the reason for that is that the testing story for debug info is really not the best at the moment. It's often quite manual and doesn't really cover all aspects. And so just to pick on an example, one of the tools that's called Dexter that's used in the LLVM code base allows you to sort of take a single test case and then kind of annotate out, like, I expect the debugger to see this value on this line. And so that works as an sort of end-to-end integration test, but it's quite manual. It doesn't and you have to just keep creating individual test cases. More recent work does sort of bring some optimization or some automation to the problem. So there's a few recent papers that do try to apply like CSmith and other automated test generation tools to cover more things, but they don't really check values very precisely. So they're just really looking at, is this line one of the possible lines in the program, or is this value some possible value? It doesn't really check precisely what value do I expect on this line in this particular block of code. So our sort of claim here is that having a stronger testing story would really help catch a lot more of these compiler bugs that affect debug info generation, and then that, in turn should lead to a more reliable debugging experience overall. And so one of the ways we could go at this is by applying KLEE to sort of check this information more systematically. So if we had some way that was more automated and systematic, we could be applying test generation tools like CSmith, and then also seeing much more usable results about what those values actually mean. So if we look at this small example of LLVM IR at the bottom, that's just showing you that it computes a shift left on some input value that could be symbolic, and actually makes use of the debug info mapping that exists in LLVM IR. If you compile with debugging enabled, you get these little sort of mapping assertions that say something like that %mul result is actually mapped to the source variable X. So you can kind of combine the facts in that tiny program there and see that, as KLEE was executing that small bit of code, it learned that the source variable X should be equal to this symbolic value. And so, putting these bits together, we can kind of try and start using KLEE to learn things about the debug information in the program. And then quickly kind of just talking a little bit about the way debug info looks when you compile down to the binary. Now, I don't know how many people have looked at debug info in depth, but one of the interesting things about it is that it's actually quite a sort of very powerful stack machine in the drawer format that's typically used on Unix systems that can actually access registers and memory and do little computations when it's trying to work out what the values and locations of variables are. So in that example there, this is just a simulated example to kind of demonstrate the power of it, but it's saying there's a variable y, and there's one code region where it's got let's see, here, maybe I can use this crazy pointer thing. Okay, yeah, okay, so this first block there, it's saying there's at those instructions, the variable y is stored at an offset of the base register of the stack frame. Then there's like a second set of instructions where there's no location emitted at all. So if you had stopped the program in that area, then that's one of those cases where you wouldn't be able to access that variable value at all. And then there's another region where there you're seeing kind of a slightly more complex formula where it's taking in a certain variable or a certain register, doing some computations, and then returning actually like a literal value that it's computed on the stack machine for Dwarf. And those, I mean, these really do happen in real programs. Often, you know, an optimizer will apply some transformation and it realizes it's able to sort of capture the value of the variable using these somewhat more complex debug expressions. But so looking at these expressions, we sort of started to realize that there's kind of some resemblance between the sort of symbolic mapping of variable storage and KLEE's own kind of symbolic values that it captures during execution. And so can we use those things we've kind of gleaned from looking at these examples to build something that can check the correctness of the debug info? And we'll talk about that now. So the kind of basic approach we're using at the moment is we take some C program, could be any program, it doesn't have to be a test program you've annotated before, just any randomly generated program from CSmith or some other tool. And then we're going to compile that twice. So we want to look at the unoptimized version and an optimized version. And we're basically kind of treating we don't have any oracle for correctness here. So at the moment, we're just sort of assuming that the unoptimized version is the correct debug info, which is often the case, of course, not always, but for our purposes, we're assuming that that's correct. And then we're trying to compare those two versions of the program and look for consistency between the unoptimized and optimized versions. And so what does consistency check mean? What does that mean here? So we want to sort of, for each function independently, just look at a single function at a time, collect the symbolic values as KLEE normally does when it runs through some code, but then lift those up to the source level so that they match kind of the view that the programmer is typically working at. And then we also need to be able to like relate these two programs together. So we'll extract certain features from the programs at the moment, namely the sort of the source assignments. So where the source variables are assigned in each program, and we can use those to kind of relate the two programs together. But one thing I want to kind of highlight here is that this is quite an unusual application of symbolic execution. It's quite a bit different than the kind of typical case of trying to find some program property across all possible paths. We actually don't really need that level of sort of execution here for checking debug info. We really just focus on a single function at a time, and then treat all other treat the inputs as symbolic, treat function calls as kind of a symbolic thing that we update state as needed. Only visit each basic block once or a few times to just gather these quite general symbolic values that are really enough to check the correspondence between the two versions of the program. Right, so let's go through an example to sort of talk about how this would work. So we'll look at the unoptimized version and optimized version and compare those. I do have another example, but there's not enough time for this in the main talk. So anyone who's curious about more details, we can maybe go through the second example. But right, okay, so this is the same C code from the start of the talk. That's just a simple loop there. And then on the right, we have the unoptimized, hopefully that's mostly readable, I think. Okay, yeah. Unoptimized LLVM-IR on the right. And so the kind of the key areas to look at there are at the top, we have the alloca instructions that's kind of creating some storage space and saving a pointer to store a variable in. So it's creating a storage location named %y there. And then the debug declare assertion is one of these debug mappings on the next line saying that the LLVM-IR value %y, whatever is stored there should be treated the same as the source variable y. So it's a little confusing with two different y's flying around. But and then you'll see there's several points in the program where something is stored to the pointer in %y. So those are basically treated as assignments to the source variable y because of that mapping there. So at the top, in kind of the early bit of the function, we see we're storing a constant 0 to the source variable y, and then as you go through the loop, we're updating the value of y as we would in the loop, and you see a store down at the bottom of the loop there and the IR side as well. And then if you just go through this loop a single time, so just one time through each basic block, these are the like a simplified version of the symbolic formulae that KLEE would capture. And so I just want to emphasize though that this is like a dynamic execution trace of the program, but just going like a few times, either one time or maybe a few times as needed through each basic block. Now let's look at the same sort of thing for the optimized version. So as I hinted at earlier, if you stare at this long enough, you may have worked out possibly that this is, that Clang has totally unrolled the loop, and so this actually becomes a constant computation. But unfortunately, what's happened here is that the debug info has kind of gotten a bit lost along the way. It has worked out okay for the top bit. So the debug mapping is slightly different in this case. Before we had a debug declare, now it's saying debug value. It just means, debug value just means the literal value of the source variable is this thing that I've put in there. So now it's saying at the entry point, again, y is set to 0, that part is correct. But then for the later on bit in the loop, unfortunately, first the mapping itself has become kind of totally detached. So the debug value down at the bottom there says undef. That means, so it's like no longer really attached at all to the IR results that's actually being computed. And also many of the IR instructions are attributed to the wrong source line along the way. So unfortunately, this is just, this is effectively a bug in Optimizer somewhere along the way. It got confused about its debugging for handling, or decided to drop something because it wasn't sure how to preserve it. And so then if we take both of these versions, that's kind of the core of what our approach of checking this is doing. So we're looking at the assignments we've captured in the unoptimized version and the ones we've captured in the optimized version and comparing those. And so if we do that, kind of as I said, we see that there's different source lines in the optimized version and that a mapping was lost. So that points to an inconsistency and a compiler bug that we could then file and hopefully get fixed. Right, so then overall talking about kind of the status of our approach. So we have the core of this approach implemented in a new tool that builds on top of KLEE, and then it just expects 2 LLVM modules. So one before and after optimization that you've arrived at through whatever build process you want to run, and then just applies these checks as I've described. So looking at whether the variables have the correct source lines in both cases, and whether the assignments match up once you've run them. We'll run KLEE on both versions and then kind of use the internal solver to check that they are giving you a consistent formula that equate to the same thing, or that are consistent. Right, and then so going off from there, we still have a bit of work to do to kind of add support for some more complex debug mapping cases. It does get a bit more complex than the story I've outlined here in the slides, but so we need to add support for those so that we'd be able to actually run through larger real programs. Also, we do need to actually build out this function independent mode that I kind of hinted at earlier to keep the state space contained and avoid sort of some of the path explosion problems that can happen. At the moment, we've just been using kind of self-crafted small functions, but actually, even that has been enough to find compiler bugs. It's surprisingly easy to find compiler bugs with debug info handling. Like just entering like a basic loop that you would think should work just fine. Nope, the debug info disappears. So, or is wrong in some way. So the fact that it's so easy to find those, just typing in things that you can come up with in your head suggests that there will be many more bugs revealed. And from previous knowledge, I also expect from the way that the optimization path is handled debug info, I expect there are many more cases we will find once we start applying automated tools as well. And then we also like to kind of gather debugability stats across optimization passes in LLVM to see sort of which passes have more of a impact on the debug info. Are there some that just kind of constantly throw it away every time they run, or that sort of thing? And then probably as future work, a first submission here is we'd like to expand this also to cover the machine code generation phase. So the current approach just covers the optimization phase of the compiler, and so there could certainly still be bugs in debug info handling after that, right? After optimization and into the machine code phase. So we'd hope to handle that as well by lifting things back up to the LLVM IR level. And yeah, just to summarize things, so the debug info often gets lost in optimization, and that's frequently what you're seeing when you try to debug an optimized program and get all these kind of variable not available messages. Part of the story there is that the current testing approaches for debug info are not, they're hard to use, or they're manual, or they don't check values very precisely. And we claim that comparing the symbolic values that we're getting from KLEE will really help give sort of both an automated approach that can then leverage test generation, but also more precisely check the value correctness as well compared to previous approaches. And it also it relies on this possibly surprising connection between the semi-symbolic or debug location mappings in Dwarf and KLEE's own symbolic values during execution. So yeah, with that, thanks for your attention. Happy to take any questions.